Okay, here's a problem from clearly chapter 14, fundamental problem 14-6, the last one of the section, so maybe that means this is the most difficult one of the section, I don't know. But let's see how we can use the work and energy principle to solve this problem here. Read it together. The 5-pound collar is pulled by a cord that passes around a small peg at C. If the cord is subjected to a constant force of 10 pounds to the left, as you can see, and the collar is at rest when it's at A, determine its speed when it reaches B. This is a great problem for us to solve using the work and energy principle because it involves three things: force, velocity, or speed, and distance. Notice that we don't know anything about time in this problem. They don't say 4 seconds later, 2 hours later, or anything like that. Everything that is provided for us is in force, velocity, distance. If you see that, then you can immediately jump to work and energy. There's nothing in the work and energy equation that has to do with time, only with force, velocity, and distance. Let's write down what is given. Never hurts to start there. What is given? The weight of the collar is 5-pound force. That is the weight of the object. It passes around a peg at C. That's over here. The cord is subjected to a constant force. F is constant, 10-pound force. And we also know that the speed of the collar at A is 0. What are we trying to find? Well, we're trying to find what the speed of this stinking thing is when it reaches B. When it's over here, how fast is it moving? Here, BA is equal to 0. It's at rest. But then we start pulling on that cable, 10-pound force, constant. How fast is it moving? All right, well, once again, this has to do with force, velocity, and distance, so we turn to our work and energy principle. Work and energy principle says that your initial kinetic energy plus the net amount of work that's done on the object is equal to your final kinetic energy. Another way to write this is 1/2 mv, I'll say a squared, that's where it is initially, at A, plus the net amount of work as it goes from A to B is equal to 1/2 mvb squared. Well, immediately, one of these values goes to 0. The object is at rest at A, so that first term immediately goes to 0. But it speeds up. We know that at B, it's now going to be traveling at some new speed, meaning its kinetic energy will not be 0 at B. The only way that that can happen is if we put a net amount of work into the system. Doesn't hurt to draw a free body diagram. In fact, I encourage you and require it. Here's the collar, right there. There is some force that's equal to 10 pounds pulling down. There is a weight force downwards, and there must be actually a normal force that keeps that collar from falling downwards, right? That's the force between the collar itself and the shaft that it's riding on. Now here's where it gets kind of tricky, because you see that force is making an angle theta with the distance that it's moving in. It's going to be moving to the right, like that. Uh-oh. Freebody diagram also requires us to indicate our coordinate axes, x and y, like that. Okay? But the reason why this object speeds up is because of this force, 10-pound force. It's not because of the weight. It's not because of the normal force. Those two forces are always perpendicular to the direction of the motion, so they don't do any work. The only work that we need to consider is the work that's done by that force. Well, what is the work done from A to B by that force F? What's the work done by that force F from A to B? Well, it's pretty tricky if we just consider how I've drawn this free body diagram over here to the right, because that angle theta that I drew will change depending on where this object is in its rotation or in its position. As its position changes, that angle opens up. It gets bigger. Oh man, that's going to make our equation pretty hard to work with. Or does it? We know that this collar is going to move some distance. It's going to move a total of 4 feet to the right, like so. This distance, 3 feet, is constant between the peg C and the shaft itself. Aha. Here's the direction of the force. That is also the direction of this string. They are in perfect alignment. So the work done by that force is going to be the magnitude of the force times this distance s that the string elongates by, okay? That distance s as it moves to the left. They're both in the same direction, so that means it's going to be a positive net force, or positive net work. Positive net work. I know what that force is. That's just the magnitude. It's constant. It's 10 pounds. How about that distance s? What is that? How far does this string get pulled? Well, that string gets pulled the difference between this distance here. This is the original length of the string, which is 5 feet, and this distance here, which is 3 feet, right? The original length of the string there was 5 feet from the peg at C all the way up to A. That's 5 feet. And then when it's at B, it's only 3 feet long. So that means I must have pulled the rope a total of 2 feet. Total of 2 feet. Aha! So UAB is going to be equal to 10-pound force times 2 feet. That's 20-pound force feet. Okay, let's remember that. Take this to a new page. All over again. TA plus the net work done from A to B is equal to TB. TA is 0 because the object is not moving. The net amount of work is 20-pound force feet is equal to 1/2 the mass of this object. Ooh, I don't know what the mass is, but I do know what its weight is. And I'm going to assume that we're doing this on Earth. So the mass of this object is 5-pound force divided by 32.2 feet per second squared. This collection of units is equal to a slug, which is the base unit for mass in the English engineering units, times VB squared. Now all we have to do is plug this into our calculator. 20 times 2 divided by 5 times 32.2. And we take the square root of that value, and I find that it's equal to, VB is equal to 16.05 feet per second squared. Do a little dimensional analysis right here. On the left-hand side of this equation, I have pound force feet. If VB is in feet per second, when we square that, that's going to be feet squared per second squared. I multiply that times pound force divided by feet per second squared. I'm going to be left with pound force feet. The right-hand side is in pound force feet, just like the left-hand side. VB must be in feet per second squared. Oh. Bah. Feet per second. Whew. I'm not talking about acceleration. VB is 16.05 feet per second.